Hello and welcome to Topic 5 in Materials Engineering 310 and 350 on thermal properties of polymers. This is part 1 of the lectures. In this part we'll be talking about the basic concepts behind thermal conductivity in all materials. And then later topics or later parts of the lecture we'll get into discussion of polymers specifically, as well as how we test polymers for thermal properties. First of all, remember that in heat transfer there are 3 basic modes that heat is transferred: conduction, or the direct transfer of heat through a material; convection, or the movement of heat via air currents; and radiation, which is the transfer of heat through photons being emitted from a radiative source of energy. Now, in polymers we are interested primarily in the conduction of heat through a solid or viscous polymer melt. The convection and radiation really have to do with travel of energy through air, and we'll leave that for another discussion. There's 2 basic conditions under which heat is conducted through a material: non-steady state conditions and steady state conditions. In non-steady state conditions, the material is heating up and increasing its temperature gradually as it tries to reach a steady state condition. At steady state, the temperature gradient through the material remains constant. So in a non-steady state condition, when the temperature starts out at low values and gradually increases through the material, the amount of energy stored per unit area is given by this following equation, where the Q is the heat transferred through the material, is equal to the density of the material times the pressure constant specific heat of the material times the change in temperature. Keeping in mind the density of the polymer is around 1 to 2 grams per cubic centimeter, and the specific heat is between 1 and 1.7 kilojoules per kilogram degree Celsius. Once steady state is achieved, heat flow begins to follow what's known as Fourier's law. In this case, the heat flow Q, at least in the x direction, is equal to minus K, where K is the thermal conductivity, times the temperature gradient, or the change in temperature with respect to change in distance. In the x direction, the thermal conductivity for polymers is typically 0.15 to 0.6 watts per meter per Kelvin, and dt dx is assumed to be a linear gradient. In other words, dt dx is constant. It's the slope of the line as you go from one side of the material to the other side. We can combine these 2 properties, the Q value and the non-steady state conditions and the Q value in steady state conditions, and calculate something called the thermal diffusivity. And thermal diffusivity is a key property in transient or non-steady state heating because it expresses the rate at which heat permeates into the material. The symbol for thermal diffusivity is alpha, and it's equal to the thermal conductivity K divided by density times specific heat. Typical values for diffusivity are 0.1 millimeters squared per second for polymer melts, and a lower value of 0.07 to 0.2 millimeters squared per second for solid polymers. You can calculate alpha in CES using the advanced equation builder. Please ask to see how to do this if you're interested. Here's a plot of the thermal conductivity of polymers from CES versus the calculated value for the thermal diffusivity. And what you can see is that for most polymers, the values tend to follow a linear relationship. That is, as thermal conductivity increases, thermal diffusivity increases proportionally, which is what you'd expect given the equation in the previous slide. One last interesting note: heat transfer and diffusion are related concepts. Both follow something similar to Fourier's law. Heat transfer has Fourier's law, in which the heat being transferred is equal to minus K dt dx. In steady state diffusion, it follows Fick's first law, where the steady state diffusion flux is equal to minus d, the diffusion coefficient, times the concentration gradient, dc dx. In non-steady state conditions, the distance that heat travels into the material is proportional to the square root of the thermal diffusivity alpha times the temperature T. In non-steady state diffusion, the distance that an impurity species travels into the material is proportional to the square root of the diffusion coefficient times time. So there's a lot of similarities between diffusion and heat transfer in materials.